Okay, I hope you all see my slides.
Yes.
Yeah, it works. Okay. I know it's hot, at least in Krakow, because I'm based in Krakow, and it's like for probably most of you, like the afternoon. And yeah, the topic we chose is not the easiest one. So I promise I will try to be gentle. And yeah, I'm after like 8 hours of work, so uh, we are all in the same situation, drinking water and enjoying discussions about concurrency. So the topic of today presentation is Java concurrency. I will focus, of course, on Java util concurrent package from JDK, but the main focus is how to write better concurrent code using what's included in Java. So I would not focus on like fancy things like akka, the actor model, or reactor, or and any other fancy things that you can do using different frameworks, because there is a lot of goodness, I think, in Java util concurrent. And what's funny is most of these frameworks like Akka or Reactor are just wrappers trying to apply different approach, different concurrency models, but underneath they use the same things, so the Java util concurrent package. Uh, yeah. Uh, so a little bit about me. Okay, it's here. So yeah, I work at Neo4j. This is my seventh year at the company, and I work in the database benchmarking team. So I'm responsible for with my team for benchmarking the core our product, so the database. Uh, and yeah, I should remove this slide. Actually, every time I read like I'm 20 years with JVM, it makes me feel older, unnecessary. So yeah, I started with Java 1.2, I think, in 98, 99, something like this. Um, and yeah, with some breaks and hiccups during my career, uh, doing different stuff. I was always coming back to JVM and always doing things around performance and benchmarking. So I ended up in the benchmarking team at some point of time because previously, before I was doing, microservices and all this new stuff, but I'm more interested in these things. It's okay. Let's start. The thing about concurrency is it's the same about performance, that people keep repeating the same sentence, that concurrency is hard and concurrent performance is hard, and it's really non-trivial and hard to work with. So, and if you as a junior hear these words, it's like you are instantly you get scared and you don't explore this field. And I think the part of the reason I'm doing this talk is I want to bust some myths and legends and misconceptions. And I think it's all about the proper mental model and proper abstractions. Of course, it is still hard because at its heart, the problem is hard. Uh, because you will deal with low-level hardware constructs and details, and to understand concurrency, you kind of need to understand hardware. You cannot disconnect these two things. At least what I think is the hardest thing for software developers is thinking about hardware. So I would try to make it a little bit simpler, at least in the context of Java, because Java, for some reasons, is specific in the concurrent world, and make it a little bit faster. I mean, easier for you, and maybe you will start exploring these topics because I find it really interesting. Even if you don't do really hard concurrent problems at work, I think it's still fun to explore. Okay, so the presentation has two parts. I think this first part is like, 15 minutes, where we need to agree what we understand when we say concurrency, and also we need to understand and agree what is the concurrency model JVM and all the JVM languages employ. Okay, so we can start with formal definition. Its concurrency is ability of different parts of the programs to be executed independently or simultaneously. Okay, so it's about running parts of your program out of order on many threads. But the thing is really important. If you have your program and you run it concurrently, you have the same output as running it on sequentially. Yeah, so you just change the execution model. You expect the outcome to be the same. Okay. So depending on the implementation, it can be, executed out of order. Uh, some parts of the program make progress at the same time, and of course, you can use multiple CPUs, multiple hardware threads. This is for me like the best explanation. This is concurrency. So you have the shared resource, and your shared resource is memory or CPU. Okay, and many threads are like fighting like these players for access to this shared resource. It can be anything. It can be disk. It can be file. It can be CPU. It can be memory location. And parallelism is a little bit different because you execute multiple things at the same time, but because you have multiple CPUs uh, and you don't share, that's like really important property of parallel programs. You kind of don't share data structures. Of course, as long as you read, it's fine, but you don't have data races in parallel programs. Yeah. So that's like the most important difference between, because sometimes people interchange these terms, but they are different. So why we are even talking about concurrency? The thing is, and I highly recommend to look for this article by Herb Sutter. I think it's 2002 or 2003. The title of the article is "The Free Lunch is Over." And it was written in a time when first multi-CPU, multi-threading CPUs hit the market, consumer market. And what Herb was trying to say in his article is, until like late 90s, if you wanted to have your program to run faster, you were just buying faster CPU. Yeah, more clock, faster clock, everything was faster. The problem is that when we run into territory of having multiple cores and running concurrent programs, then the thing is, the more core you have doesn't necessarily mean faster. And this is the whole like message from Herb, who's at the moment, I think he's a chief of C++ committee, or even like some really important figure in that C++ committee. He was saying, you know, in today's world, if you want to run things faster, you need to also understand how to write concurrent code, because things don't get faster because you have multiple CPUs. You were able to scale by having more clock cycles, and it didn't require any work from the programmer. But with multi-core systems, you need to do some work to change your algorithms, change your data structure to really benefit from having multiple cores. So that's why it's important. If you want to scale your software, you now need to understand. Some work is done by frameworks, but you still need to have understanding how it works. Okay. So I highly recommend both articles. The free lunch is over. This is the original one. And the second one, I think, was like few years later, also written by Herb about, that we have supercomputers in our pockets, basically smartphones, who run multi-core programs and are multi-core systems. Uh, and part of the Herb article is that the thing that why we think the concurrency is hard. Because as humans, we think sequentially. We are, except some people, uh, in the field, regular, normal, healthy programmers have single core, like single brain, and we think about our problems as a sequence of actions. So it's really hard for us to build a mental model, but some things can happen out of order, or some things can happen at the same time, and it's really hard to reason about the concurrent programs. That's really, really, very hard. And another thing is it's really hard to test it, and it's really hard to find all the problems uh, because so many things impact how your program at the end is executed. Because the CPU can reorder instructions, your compiler during compilation can reorder instructions. And this the operating system at any point can give and take CPU time to your program. So there are many factors out of our control, and we still need somehow to reason about it, even if we don't have control, because the compilers, the branch prediction on CPUs, all the things, fancy things on CPUs and so on, can reorder your program, change order of instructions, and we don't know. Why it's so hard? This is like my own thoughts after all these years. Is like I blame cloud kind of because as software developers, most of us don't care about hardware because we have Kubernetes, we have cloud, AWS, and scaling is really simple as long as you have a credit card connected. You just click, create new instances, change instance type, and you're happy. We don't like to think about hardware. Uh, the second thing is what Helpsatter wrote about sequential. And the third thing is this is a really nice presentation by Nitzen Wackert. It's called Illusion of Execution. We write programs sequentially because this is how programming languages are constructed. You write sequence of actions, commands, but you never know how they will be executed. So the problem is that I just written a couple of things that can reorder your program, but it can be memory ordering depending if you are on ARM or Intel CPU. There are different rules, about how the order of operations will be at the end. How what CPU will do and in which order will execute your uh, your instructions. Then you have memory hierarchy. So you have now, memory, and because access to memory is slow, you have caches, and you have multiple layer of caches. So you actually don't know if the value you written is visible to others because of the many layers of caches. We all have different protocols in CPUs. Most of them some implementations of the MESI protocol. Uh, and you don't know how threads cores agree on the value you're written into the memory. And of course, you have compiler optimizations. So in this jungle of different things that can impact your program, we as programmers need some kind of formal model to say, okay, if I write this program like this, I can expect this outcome. What is this formal model? So it's called memory models. Uh, And you can think about memory models as a kind of contract between you, programmer, developer, and the hardware manufacturer and the compiler writer. Okay, so all of the three parties, an operating system, So all the parties uh, agree on some rules, some contracts, that if you execute instructions in this order, you can expect this outcome. So this is what memory models are about. Why it's important? Because since Java 1.5, so ages ago, uh, Java came up with this idea that, okay, we need some kind of formalism, formal rules saying how our concurrent program will behave. So programmers can write predictable code. The problem is that this model is really complex, and I call it Alexei Shipylev paradox. Alexei Shipylev is one of the guys working on JVM. And the paradox is, once you understand, you lose ability to explain it. So I would try to explain it and see how it goes. Okay. Because I'm kind of really like pragmatic guy. I love theory, but I write code to make money. So theory is interesting, and theory can be sometimes a trap. Because if you go into the formal Java memory description, the Java memory model, you will find things like terms like program orders, synchronization orders, synchronize with relationship, happens before relation, and then you will find the sentence that all of these things are transitive closure from the set theory. That's me trying to understand it. Yeah. And the problem is, and I made this mistake a couple of years ago, but I started from reading the formal models and mathematical models and trying to understand it. And I learned that what I need is to actually focus on the side effects, not the implementation, because I'm not writing JVM, I'm not writing compilers, I am the client. So I need to understand the rules and expected results, not necessarily the whole formalism. You will get this presentation. I will kind of skip this part because I want to focus on code, but you will see a lot of references and articles worth to read to get deeper into like super deep into this. But I will try to explain it like, as you can see, this is my story trying to understand Java memory model, reading some things and not understanding, trying to read something once again, how it works. The essence of the Java memory model is something called happens before relation. So if you start reading about it, I think this is the key to understanding. And this is the level of abstraction should be enough for most of us as developers. So what is the happens before relation? Because if you even read the Java docs of some classes in Java, you will find this, oh, this method forms a happens before relation with something. This action is a happens before relation with the other action. So the happens before relation is basically really simple. It says that if A, sorry, my Polish, if A happens before B, it means that B being the action, so method call, access to a method, actually access to a memory location. If A happens before B, the B will see all memory changes that happened before A. So if you write something to memory and this write operation happens before relation with another operation which is reading from the same memory location, by Java memory model, you are guaranteed that all the actions before A will be visible to action B. And that's like the essence of, like the heart of Java memory model. Okay? So it means that if one thread writes one variable and the other threads reads this variable later, then because there is happens before relation between these two, second thread will see all the changes to other memory locations done in thread one. Okay. I would need to see your faces like, okay, yeah, I understand. Just write me. It's cool. I understand what's going on. So, and if you go to this article by Alexei, he will say that this is sometimes referred to safe publication. Uh, so it's publishing the changes to memory done by one thread to the other threads. You can think about this like that's another like abstraction mental model you can use. But by writing something, you publish this change to other threads, other CPUs processes. Of course, not all actions in Java have happened before relation. Of course, they could, and you could do it really simple. Make everything volatile. Yeah, put on every single field and every single variable a variable volatile modifier. Okay, and if you put volatile on a field, it means that writes and reads have happens before relationship. Without it, they don't. So if you don't have volatile on your field, you can see processors, CPUs, threads can see different random values. Even if you wrote something to memory location, if they are not volatile, you can see any value. Why it's so? Why not everything is volatile by default? The answer is for speed, because in most cases you don't need it. Okay, in most cases you don't need this visibility. You don't need safe publication, and the problem is if you enforce safe publication, if you enforce volatile everywhere, the compiler cannot do optimizations. And also the CPU, it will say, okay, you want volatile, so I won't optimize, I won't do prefetching, I won't do branch prediction. You stop optimizing your code because what you value is consistency. Yeah. So that's why by default there is no happens before relation in Java, unless you mark something volatile. What is interesting is this happens before actions are defined in JVM specification. And for example, volatile read followed by volatile write happens before. When you do synchronize section enter and exit, so if you enter the synchronized section, exit the synchronized section, it's guaranteed that other threads will see what happened before the enter before the exit. If you enter, it's guaranteed that you will see the latest values. Okay, it's the same with log require and release. If you release, you do safe publication, and other threads will see all the changes made in this thread before you did the release on log. And when you acquire the log, it's guaranteed that you will see the latest values of your shared memory uh, what happened before acquiring the log. Okay, there are many more things that have happens before relation, but they are like I want to really focus on pragmatics of this. So there are the most common cases: volatile reads and writes, synchronize enter and exit, and log acquire and log release. Okay, let's go to the code because enough theory. The thing is that once you understand the happens before, you can start building your concurrent structures. And of course, you can write something, build something with your bare hands. But what I think is underappreciated is java.util concurrent. I think about it like a box of Lego blocks. Okay, so there are already structures implemented, different things like different logs, different kind of queues, different kind of barriers, atomic operations, executor, and so on and so on. And all these structures are like you can use to build your own concurrent structures and code. And this is what I would like to focus for next, like I would say half an hour. Okay. We'll focus how to use the primitives. Usually they are called primitives from Java Concurrent, the concurrency primitives to build concurrent code. Okay. What is interesting is you will find it in Java docs. Yeah, if you go to Java docs, you will see something like this. This is from, for example, concurrent linked the queue. It's that whereas in documentation in Java docs, it say that putting something on the queue has happened before relation with removing something from the queue. So if you put something on the queue and then other thread removes this from the queue, it's also guaranteed that all the things that were changed before writing to the queue are also visible to another thread. Okay, so that's really important to look at Java docs because all the structure is Java concurrent describe which operations, because not all operations create happens before relation, what operations on this data structures form the happens before relation, okay? It's like another example is concurrent hash map, is if you put something in concurrent hash map, it is happens before relation with getting the same key on the hash map, okay? Okay, so let's go through examples. I think we'll have like time for sure to focus on the object pool and actor model. You know, originally this presentation is like 2 hours long. I will share code and I will share slides, so you will have fun. I think the key are these two because they are really interesting beasts. So what we'll try to do is implement some data structures and some algorithms, concurrent algorithms and concurrent data structures just using java.util.concurrent, okay? So let's start with really simple example, at least at the concept level. Let's build concurrent object pool, okay? So let's define some requirements. What we expect is that we will build concurrent object pool that will have minimum and maximum capacity. So we'll have like some number of objects in the pool with maximum and minimum capacity. So initial capacity. The pool will create object on demand. So every time it will need a new object and it will be below maximum capacity, it will create a new more object and will make sure that we always have minimum amount of objects in the pool. And what is interesting is before returning the objects to the pool, we will check if the object is valid. If it's not valid, we will not put it back in the pool. Imagine like, okay, we have a connection to database and the connection is broken. So we don't want broken connections in the pool. Yeah, so we will throw it away and just recreate a new connection if needed. So these are our requirements. And this is how I usually think about concurrent programs. Yeah, we start from the requirements and then I try to think about properties of the structure. So what are the properties of this pool? One property is that only n, so the maximum capacity of the thread of the object, only n threads at the same time can access the pool. Okay, this is one property. So if you have maximum capacity of 5, only 5 threads at the same time can access the pool. If we have 6 threads, he needs to wait until the one of the threads leaves the pool and then the next thread can enter. Yeah, that's one of the property of the pool. The other property is that resource can be borrowed by only single thread at a time. So if we have a connection and we get this connection from the pool, only one thread will get this connection until it's returned back to the pool. So two properties of the object pool. And then you say, oh, okay, you can get into panic mode if you get such task in your Jira or whatever you are using. Or you can say, actually, in java.util.concurrent, there are two things that have these properties, okay? One property is Semaphore. One data structure is Semaphore. It's not data structure, it's a barrier. So the property of a Semaphore is to protect resource from accessing the resource by more than n threads, okay? So Semaphore will allow n threads to enter your critical section. And then there is a queue, and queue is satisfying this property that only one resource can be borrowed by a single thread, because we have first in, first out. If we take something from the pool, it means nobody else can take it, so we are safe. So we can start thinking about implementing the object pool using Semaphore and queue from java.util.concurrent. Okay. Let's go to the code, actually. So what I can do, here is my pool. Yeah. So I need my object factory, so something that will create objects. It can be connections, it can be anything, some heavy duty objects. So I need some kind of abstraction to create new objects. I need an abstraction that will validate the object before entering, returning it back to the pool. So we need something that will say, okay, this object is valid, it can go back, and I need minimum and maximum capacity. Yeah. So look what we have. Like, we need a blocking queue and we need Semaphore. The blocking queue will keep the objects in the pool, and Semaphore will make sure that only maximum number of threads will enter the pool. And of course, if you take a look at this, the Semaphore property, the max capacity is the size of the queue and the number of permits in the Semaphore, okay? And then, okay, we have the factory validator. We prepopulate our pool in constructor. Everything is fine. So we are creating stuff and putting it on the queue. And then comes the interesting part, is the concurrent code. So what happens on borrow? Yeah? On borrow, we say, okay, we say Semaphore acquire. So making sure that there are no more threads than we expect the maximum size of the pool. If there are more than expected, we just simply block here. Yeah, it's like lock, but not exclusive. Yeah. Then we take the resource from the pool, and what can happen? We can have not enough resources. Okay. So if the queue is empty, we say, okay, we create the new one and just simply return to the client code. Because we do acquire here, we will not create more elements than is maximum capacity of the pool, okay? So already like Semaphore is kind of guard for us to not create more resources than the size of the pool. And what happens on release? On release, we do a really simple thing. If the object is valid, we put it back on the queue, okay? If the object is not valid, we do another check. If we have reached minimum capacity, because if we reach minimum capacity, we need to recreate the object, okay? And then we do Semaphore release. And remember the happens before relation. So the Semaphore acquire is a happens before release, and resource pool has a happens before the offer, okay? So take a look at the symmetry of this code. You first do acquire, then do polling, and then when you have like symmetrical operation, you first offer and then you release Semaphore. If you change the order, things will explode. But you make sure that if I poll something, put something on the queue, for example here, new object, if I go here, I will, if another thread invokes this object, I will see the value, okay? That's the beauty of happens before. But any change that happens before will be visible to the other thread. Okay, I hope you're with me. Okay, I'm just checking. And if you have any questions, just write in the chat. I will try to answer. So what is my, after all these years, approach to writing concurrent code? Well, it may be funny, but it works for me. I always start with the single-threaded tests. So I write concurrent code, I design this code and, write concurrent code. But when I write, when I start to test it, okay, as I start with single-threaded unit test. Because if the code doesn't work for single thread, what is the point testing it multi-threaded, yeah? And it will be even more and harder to reason about if we run it in multi-threaded environment. So first, make sure that your code runs for a single thread, okay? Then we need to somehow verify that this code works for multi-threaded. And I will show you a tool in a moment. that helps you verify your multi-threaded programs. And then at the end of the day, because I work in the benchmarking team, I would write micro benchmarks to verify performance. But this is the order. Uh, if you reach limits, how to unblock? Yeah, it's a really good question. Mm. If you reach limits, how to unblock the thread? So if you reach limit, you need to wait until somebody returns the resource to the pool. Okay? That's why we make sure here that if we go below minimum capacity, we always create. So if we go here, imagine we did acquire, all resources are used. So the thread stops here, okay? Then we go here and say the other thread goes here and returns the element to the queue. Then it returns take a look at the order. We first return element to the queue and then we release. So when the thread that is blocked will go here, he will call Paul, but because of the order of things we did, we first return things to the queue, then we release. We are sure that when we go here, we will get the proper value. Of course, that can be race condition because there can be more than threads than you expect, and you again return null. That's why we have this thing here, okay? To protect us from stealing the stuff from the poll. Of course, there is some fancy error here, but if you find the error here, let me know. That will be one prize. For a long time. Okay, that's so you can block with timeouts, and you can, you know, acquire. But when you do poll, you can do polling and say, okay, I will be waiting maximum like okay 5. Yep. So and I think it's of course better practice and try to avoid calling poll without timing because yeah, Yuri is right. You can block and then you ask for problems. So then if it's case, of course you need to change the logic a little bit because if you need to handle timeout exception because you know if the timeout comes, you need to release the semaphore. Yeah, it will make this code a little bit more complicated. Okay. Uh, I simplified it on purpose so we don't like about object polling. You can talk for hours. Pad is writing about the dining philosopher problem is one of the examples. Yeah, exactly, true. So, okay, you wrote this code, and you even probably wrote unit test, like single-threaded unit test. When you say, okay, in the same thread, you put things from the queue and release things to the queue, and everything is then and it works single-threaded. Uh, performance. Yeah, we can talk about it in a minute about the performance tools. So. How you verify that it works, and we'll get back to performance in a minute. How you verify that it works in a concurrent scenario? There is a tool called JC Stress, Java Concurrency Stress. And this tool is created, maintained, and designed and used by people who write Java, the JVM team. And you can use it to verify your code, concurrent code. How it works? Let's maybe take a look at this example. It is kind of similar to unit tests because you write methods, put a lot of annotation, and magic happens. So basically, you define actors. An actor is somebody doing something on your data structure. Okay. or your concurrent code. So this is my test where I say, okay, I have 4 actors, and every actor in my test is doing following thing: borrowing element from the queue, from the pool, then doing some kind of work on this resource. Of course, I pretend I'm doing some work, but I try to like replicate the scenario from real world. So I take something from the queue, I do some stuff, so I hog the resource for some time, and then I release. And what I do, I count number of successful releases. Okay, so how many times successfully I managed to uh, get things back to the pool. And all my 4 actors are doing the same thing, taking something from the queue, doing the work, returning stuff to the queue. How the test works? What you do is you write expectations. And you say, okay, I expect, oh, it's be visible here. Okay. So after the test, you write something called arbiter. This is not like training about JC stress. I just show you how to use it in the specific scenario because it can do a lot more. But what is happening? How JC stress works? It invokes these methods, the actor methods, from separate threads. Okay, and then once all actors finish their work, it calls arbiter, and arbiter says, okay, I this is my result. How many times I successfully returned something from the pool to the pool, and what is my number of elements in the pool? Okay, and we say I have maximum capacity of 2. Okay, so this is my maximum. Even I have 4 threads, the maximum what I will see is 2, and minimum what I see is 1. Okay, so what is expected? I will 4 times call this, okay, 4 times because I have 4 actors, and the size of the pool will be either 1 or 2, okay, because this is, my minimum and maximum capacity. And what JC Stress is doing is running, this is a like experimental framework, not experimental because it's the experimental code, but the way it works is by running hundreds, thousands, millions of repetitions, okay? So it runs this scenario until it breaks, okay? And then, of course, it tries to run it with different JVM settings, enabling, disabling compilers, enabling, disabling threads, and so on and so on. So at the end of the day, when you run it, I won't run it because it takes around half hour, but I can show you the example report. Let's see, for example, this one. This is the example report. So it says, okay, I was running your test with these different JVM settings, okay? And what I was doing, okay, I put actor 1 on CPU 1, actor 2 on CPU 0. So it even tries to run actors on different threads and different cores. And at the end of the day, it says how many times the actor satisfied your expected outcomes. So in this case, you can see that majority of cases, we see the case that the second resource was created. We didn't have any violations of our expected outcomes. And, in this scenario, only 200 times we saw that there was 1 resource in the pool and 4 resource returned. And in most cases, it created the second element in the pool. Okay. So this is JC stress. Another example is, okay, I'm trying this scenario when I return things to the pool and I say it's invalid. So I need to recreate the resource again. Because this is the scenario when every time I return something to the pool, resource is valid, but I need to create another scenario when we say how how the pool will behave if we constantly return invalid elements. So it's mostly writing concurrent code. You need to think about all possible scenarios and implement them in JC stress. Yeah, so I do the same. The difference is that uh, every time I say, okay, the resource is invalid. Yeah, and so it means I need to recreate stuff. This is how I test it. The question about performance. I will give you access to the repository so we can have fun. My favorite tool is, of course, JMH, uh, Java Micro Benchmark Harness. And it's, as you can see, again, really similar to JCSters in JUnit. I write my method uh, and I annotate it with benchmark. And then I say, okay, I enabled, sorry. Uh, and I say, okay, this is the scenario, run it from multiple threads. Okay. Uh, so, and then as for profilers, I use mostly async profiler. Yeah, we can have like separate presentation discussion about JMH and async, but for me, like for performance code, uh, the go-to setup is JMH and async profiler. Yeah, if it helps. Uh, Does it make sense to use JC test to write integrations? No, 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 no. So JC Stress is mostly designed if you build like, things that fit the single JVM and you build concurrent structures and concurrent algorithms. For like writing concurrency for integration tests, it's things like awaitility and actually running things from multiple threads. I don't know any good. There is some JUnit concurrent extensions, but to be honest, I haven't used it. So yeah, JC Stress is not for the databases. It's mostly for data structures and algorithms. I hope I answered correctly. You're happy with it. But yeah, JMH and performance is whole another topic. I think last year we did presentation about JMH. So if you look, you will find the recording. Okay. JC Stress and experiments. So you need to design experiments, write the experiments in JC Stress and try it and to run it. Where can we find old recording? I think Diana can help with finding the old recordings. Because I think last year we were talking about JMH mostly. So as you can see, what happens before you can try to explain. What I sometimes also do is I write scenarios in a form of this table. And I say, okay, what happens when one thread does this and the second thread does this? And you know what can happen? It helps you build your testing scenarios because then the Semaphore release can happen before Semaphore acquire because the thread scheduling. The resources poll can happen after resources offer. So by simply uh, should object factorials, yeah, you don't have to. You don't. I don't think it should be thread safe because the thread safety is managed by the pool unless you have unless your object factory have shared state. So there's a one condition, yeah. If the object factory maintains state, it's not pure like lambda function. Yeah, but it shouldn't like factories suggest that you just create object and you don't maintain state. If your object factory will maintain state, then of course it should be thread safe. That's true. But by design, by contract, the object factory should be not blocking. Like if you look at the object pools, it's always like recommendation that object factory are fast and are not blocking and don't maintain state. Yeah. Ooh, okay, we can leave this answer. Yeah, so Sergi is asking how to create a CountDownLatch test. So basically what you do, I can do it for you. You write two benchmarking methods. Benchmark. Sorry. Responding to the question, let's try this. Yeah. If I do like this, okay, and for example, yeah. Oh, we can keep it. So if you want to write asymmetric tests, you can have two methods. Okay, that's one thing, and both methods can be doing different things. Like one method can be inserted to the queue, the other method can be getting things from the queue, and they will be run at the same time. Okay, by JMH, and of course, you can say 20. Okay, here, and then you can say, and this method will be run from 10. Okay, so it means if they are in the same group, they will run at the same time, and using the thread annotation, you can control how many threads will be calling this method and how many threads will be calling this methods. Yep. Okay. Diana Sarah shared the audio recordings. Okay. And also, there is a way to control number of threads from the command line in JMH. Mm, uh, so you can also not only use annotations, but control it from the command line. Okay. Oof. Thanks for questions. But how we guarantee that they concurrently? They don't guarantee. It's operating system. So you need to run for long enough time to test it. Yeah, that's why JC stress, for example, there is no way to guarantee things. So JC stress takes long because they run it for a long time. Okay, thanks for questions. We need to hurry a little bit. So let's take a look at another example, the actor model. I don't know how many of you heard about it. It's like from 70s. This is like one of the approaches. I'm kind of fan of it to solve the problem with understanding and reasoning about concurrent code. And it's implemented by Erlang and Akka. Basically, the idea is that you don't have threads, you have actors. An actor is an entity that has an inbox with messages, and every actor processes one message at a time. Okay, so this is the concept of the actor model. But you have many actors. The actors communicate by sending messages to each other, but every actor can work on a single message at a time, and you can only invoke and trigger actor by sending message to it. Okay. And what can actor do? Can do computations, modify its state, can create new actors, can send messages to other actors, and yeah, what I said, modify the state. So this is the actor model. But we don't have actors. We still have threads. Yeah, we still have operating system and thread. How to implement this model using the thread model? The promise of the actor model is, the message passing is simpler and easier to understand. It is less prone to deadlocks and race conditions because the actors are isolated. You don't run the same actor from multiple threads. Everything should be fine. Okay. So what are the properties? Yeah, let's repeat the same process. Each actor has a mailbox where it has a queue of messages. Okay, it's already the description of the problem gives you the answer. Okay, so every actor will have its own queue. Every actor will process a single message at a time, which means that we will need executors, a special kind of executor that will invoke the actor only from single thread. Okay, And we want to reuse threads because otherwise, we'll run out of resources. Is actor model still better than introduction of resource? I think they are complementary. Okay, it's not like you can implement actor model using virtual threads, and there are attempts to do it. And Erlang is functional language using actor model. So I don't think they compete, they complement each other. Okay? They solve different kind of problem. Actor model is more about modeling and reasoning about the concurrent system, and virtual threads is more about execution, how threads are how things are executed. Uh, so if you read exactly what is expected is we need executor service to manage threads. We need to have queues for actors, and somehow we need to protect the actor from doing more things at a time. Oh, it sounds like atomic boolean, okay? So you take all the Lego blocks from java.util.concurrent, and let's see how it looks like. Not JC stress, I'm sorry. Yeah. So we have our actor system, we have our executor service, we have our map where we keep all actors in the system, okay? And how it looks. Whenever we create an actor, we create an actor with a link queue. So this is my message box. Every actor has a small, tiny message box. So now what happens, take into account that happens before. When we want to trigger an actor, when we want to wake up the actor, we put the message onto the queue, on the mailbox of the actor, but now somebody has to wake up, okay? Somebody has to wake up the actor to do stuff and make sure that if it's already doing stuff, to not wake it up again, because it will break the actor model. Yeah, you want one actor, one thread per actor. So what happens is I use every actor has a flag. Am I doing something or not doing something? And this flag is atomic boolean. And we use atomic boolean compare and set operation saying, okay, if the actor is doing something, is not doing something, okay, it works like this. We set it to true. It means I'm doing something, but if I was already doing something, this method will return false, okay? So this way we will know, we try to set the state of the actor to do something, but if it was already doing something, the effect of this method will be false, okay? So this way we know, okay, I was processing something, I should not. But if it happens that actor was not doing anything, so the flag was false, I call schedule processing. So I say, okay, I take the executor service and I submit a task. The task will take the message from the mailbox, do the stuff, check if I process all the messages, because in the meantime, somebody is still communicating, sending still. So I'm waking up the actor, sending the message, executing the message, and once I'm done processing the message, I check if there is still something in the queue. If my queue is empty, I go to sleep. Okay, setting this flag. If the queue is not empty, I say, okay, I still have stuff to be processed. So I schedule again myself. Okay. I hope it's clear. Of course, this implementation has has some problems. I do it like simple as possible. Yeah, it is okay to access actor. You don't access actor threads. That's the problem. You don't access. You think about actors, and every time actor can get different thread when it's waken up. So you just communicate and send message to actor, and actor will take care about which thread it will be running on. Okay, so it's okay to send message to another actor, but you should not touch the threads and stop thinking about threads when using actors. I love your questions. Don't we straight in such a way parallel processing the consequential? Kind of, yeah, kind of. Uh, it depends on how to choose the appropriate number of threads. The rule of thumb is if you have processing CPU intensive tasks, okay? So you don't do I/O, you do computation, you know, calculate image, you process vectors. You don't do I/O, you don't talk with databases, you don't talk with other services. Don't have more threads than your CPU because it doesn't make sense, okay? It will slow you down. If you do processing and if you have blocking, basically it's all about blocking. If your threads are blocking, then it's the matter of sometimes like I think the default netty configuration is twice the number of your runtime uh, of your number of your CPUs. So depending on the work, if it's CPU only, no blocking, don't give more threads than you have. If it's blocking, if it's IO, double it. And of course, measure and adjust, but like rule of thumb. So how you verified such system, yeah? It's so we are protecting the actor with the atomic boolean. We're using queue to make sure that messages are sequentially processed by actors, and we use executor to optimize. Yeah, I was also recently getting about this territory of performant cores, E-cores and P-cores, and it's like crazy complex. Yeah, virtual threads is for I/O. You don't get any benefit for using virtual threads for CPU. Nothing, none. Yeah. It's I/O. I would say blocking because it not necessarily can be I/O only because you can have some computable futures and things that are blocking. So if you do blocking operations, virtual threads can help you. Yeah, that's true. Virtual threads, if you do it right, it can be like great stuff. How you write? They broke something probably. Of course, then you go and write your test, JC stress. Uh, so you can have a multitude of different, scenarios. For example, my first scenario is I'm sending, uh, I'm sending two messages. Okay, both ask to increment the value by one, and what I expect the only value that I accept is 2. So because I send two messages to increase by 1. Okay. And I don't use atomic. If you see my actor, it doesn't use atomic. It uses volatile because I still need to make sure that the other thread sees the value. But I can do atomic increment using the actor system without using atomic operations. Okay. So this is one of my scenario. It's like if I see anything else than 2, my system is broken. Yeah. Then of course I expect messages. So you write JC stress per your scenario, and of course you need to write down all your scenarios. Like another test we can think of is I expect things to be processed in order. So I have one actor sending things. So one actor, I send 5 messages to the same actor, and I expect these messages to be in the same order. So I increment by 1. So I expect the actor to receive 0, 1, 2, 3, 4. okay? And I then validate if I received one, to, okay, I start from one. Yeah, I start from one. So then I have my outcome expected, but I received messages in this order because otherwise, I broke the promise of the actor system. Uh, of course, like another things for contention when I'm like sending things from multiple actors, so I have more than just one. So JC Stress is really good at, helping you to think about your system. I really recommend doing this table. Okay, what one thread is doing, what second thread is doing, and based on this table, write, okay, if this happens in this order, what is my expected behavior? Write scenario in the JC first. Okay, I lost kind of, yeah. Is it possible to assign specific number of threads to Java operation only so they won't be used by outer system? It's kind of, you can give the size, but this will be, of course, exclusive Java threads, but you cannot control the outer system from Java. It's no, there's no way you can do it. Yeah, is it safe? Yeah, it is safe to pass the actor reference from. That's why. So you can communicate. It's okay to create new actor, two actors, pass the reference, and then use sending messages to uh, write your own OS. Crazy. Actually, yes. But before writing your own OS, no. Okay, don't do it. Right? It may be fun. Okay. We are running out of time, guys. So this is the way you can try to build your systems from the java.util concurrent and from understanding how Java memory model works, and then using JSC stress to validate your code and JMH to benchmark your code. Uh, I hope you enjoyed it. And yeah, we still have some time for questions. How to prevent the mailbox overload? Uh, yeah, so one thing I was doing here is I used blocking queue. So with maximum size, yeah. So where can I do it? Uh, yeah. So I say, okay, the actor will and here is a nasty detail because it may end up with deadlock. Yeah, if you have cycle dependency between atomic references and you use blocking queue, you can create deadlock. So there are different approaches. Like I used to play with a programming language called Pony, and where the queue didn't have maximum capacity, and they were just dropping the messages, okay, to prevent thing. They didn't want to have deadlocks, so they said it's better to drop messages than to block the system. But here's the way, and of course you can have strategies per actor what to do if too many messages. Uh, but yeah, you can control the size of by controlling the size of the mailbox, you can control. Have you ever used Exchanger? No, never. Didn't have. Sorry, I was lying. Sometimes I use it in tests when I write concurrent test. Uh, uh, no, yeah, the actor model is influenced by Erlang, and Scala was inspired by Erlang, and this is homemade actor model just to, for the purpose of this presentation. Uh, yeah, using get and set because, uh, I only care about the previous value. Yeah, because get and set first it returns me previous value, and I only care if the previous value was false. Yeah. I don't want to have a spin log here. Yeah. I don't want to do compare and send and spin on the log. I just want to see, okay, the previous value was false, so I don't schedule a new thread for the actor. Yeah, that's I kind of I think makes things simpler. Uh, cool. Uh, I wish we had 2 hours to go for other examples, but I hope I explain things for you. Thank you, guys and girls.
Hi again, everyone. It's nice to be back. I don't know if you can see me. Let me check. Yeah, you can see me. Basically, we have 8 minutes still, so on 7 now. So basically, if you have a few questions, you still can ask them. But I see that people are writing us thank yous, a lot of thank you. Thank you for staying with us, for joining this project. Jarosław, thank you so much for being with us today and for sharing your experience and your knowledge. We appreciate it a lot. And we kind of already agreed that it will not be our last event in this year together. So I guess our participants should stay tuned and wait for new announcements. But we have actually another question. Have you ever used LA,
Pragma.
LMMAX? Yeah.
Yeah, I didn't use it in production. I kind of use it because it's in Log4j too. I know the concept, don't have like a lot of experience with it. But it's also interesting concurrency model to explore.
Also, I see the question about sharing the code. I guess during this week I'll make the mailing for all of you
Yeah,
with,
I will send you both the presentation and link to GitHub
yeah,
with
and
both.
I'll add it to the, so you'll receive an email from me with video, with code, with feedback form, so you'll have it till the end of this week. So I guess that's all questions. Thank you so much. I hope you enjoyed it. You sharing your experience, our participant gathering this knowledge for them. And yeah, I hope to see you with the next Svitla Smart Talks and have a nice the rest part of your day.
Have a nice day. See you. Bye
Bye.
bye.